Welcome to another KDM problem. This time we're going to be reviewing problem 10.3, which is in your homework. I've done some preliminary setup work, which is the same kind of thing that you will find on the test, because I've already tested you on velocity polygon and acceleration polygon. So in this case, let's go ahead and get the preliminary setup out of the way, and then we'll get to the meat of the problem. This particular problem uses a slider crank, very similar to what we've done before, with the crank labeled as item 1 or body 1, the conrod as 2, and piston as 3. You should be familiar with normal notation of 0 for the stationary point, B for our first joint, and C for our second joint. Note in this case that there is a center of gravity, G2, for the conrod. It is at the middle of the conrod. The crank is at angle 45 degrees, and the crank length is 40 millimeters. The conrod length, B to C, is 100 millimeters, and again, as mentioned, the center of gravity of the conrod is halfway along it, so it's at 50 millimeters. The crank is rotating at 100 radians per second. The mass of the conrod is 0.2 kilograms, and the moment of inertia about the center of gravity for the conrod is 300 kilogram millimeters squared. So the problem statement is this. Find crank torque T1 required for dynamic equilibrium if slider 3 has a mass of 0.3 kilograms. And also note that we are to neglect the external loads and the inertia of crank 1. So, wrote a little bit of a note here. This is kind of a nasty problem because you have to solve for the velocities and accelerations to find the applied forces. It's the whole point of dynamic analysis. But since we've already done that, I'm going to give you those required values. So, here we are. The velocities for the problem. As noted, the crank is rotating at 100 radians per second, so the velocity at point B is 100 radians per second times the length of the crank, or 4,000 millimeters per second. Doing a velocity analysis using a velocity polygon, we find that the velocity of C with respect to B is 2,948.8 millimeters per second, which means that the rotational velocity, omega 2, for the conrod is 29.5 radians per second. Finally, the velocity C is given as 3,662.5 millimeters per second. Now, using the process that you're already familiar with, I've done the acceleration analysis using acceleration polygon, and this is the table for the acceleration values filled out with the values that I got from the acceleration polygon. In this case, the things to note will be that the angular acceleration of the conrod is 2,692.2 radians per second squared. The linear acceleration of the piston is 290,167 millimeters per second squared. And the final thing we're going to need is the linear acceleration of the conrod in order to figure out what kind of inertial forces it will be generating. To get the linear acceleration of the conrod, we need to get the actual acceleration vector. Because I did this on the computer, I don't have it on a sheet of paper to show you, so I'm just going to sketch it out. As you recall, for an acceleration polygon, we take a fixed point, generally labeled O prime. We would draw then the normal acceleration for point B with a magnitude omega 1 squared times the length of the crank. That's at 45 degrees based on the setup of the problem. It's going to look something like that. There is no angular acceleration of the crank, so we only show the normal acceleration of point B, and that defines for us the total acceleration of point B. I'll label that B prime. The next thing we would put in is the normal acceleration of C with respect to B, which we calculated down here as omega 2 squared times the length of the conrod. It's 87,000, so it's only about a quarter of the length of this line, and it is parallel to the conrod. So I'll go ahead and just kind of sketch that in. This is not drawn to exact scale, it's just to show you the issues. Now we have two other accelerations that we simply don't know. All we know is the direction. Those are the tangential acceleration of C with respect to B, and the linear acceleration horizontal of the piston, A sub C. Now, we do know their directions. The piston's velocity and acceleration are both horizontal. It is a slider crank mechanism. So I can sketch a horizontal line of indeterminate length onto my acceleration polygon. The other thing I know is that the tangential acceleration of C with respect to B is always perpendicular to the straight line between C and B. I know that it starts here, and if I sketch something like a perpendicular line just by hand, I know that it'll go like that. The intersection of these points then defines the acceleration of C horizontally and also gives me the tangential acceleration of c with respect to b. And as I noted before, I already had the normal acceleration of c with respect to b. But what I need is the acceleration of this point, the center of gravity of the Conrod. It is geometrically exactly between points B and C. So on the acceleration polygon, it is also between points B and C. If I sketch a line between those two and go in its center, that is g2. If I want to get the magnitude of its acceleration, I merely need to scale the distance back to my fixed point and take it through the scaling factor of my acceleration polygon. That did give me a value here. I'm going to write it down for you. The acceleration of g2, a sub g2, is equal to 319,507 millimeters per second squared. The other thing that I can get from this is the direction of this acceleration vector. If I were to throw on my coordinate system, I have x and y here, it can be seen that my vector runs this way, and if I measure that angle, I will find that this is at 206 degrees. So this angle is 206 degrees. That's going to be important for us when we go into the analysis for the static forces or the dynamic forces on this mechanism. That concludes the setup for this problem. I'll come back in the next file and we'll start to do free body diagrams of the various components.